Part C of that question is relatively straightforward. It's just simply coming up with the propagation into that mark-to-mark distance. Or sorry, in this case, the mark-to-mark height difference. Would there be any questions on that particular one?
Well, I received a question which says October 2009, number 5. So I guess the candidate wants us to look at another exam.
Well, is there anything more for this one first?
Yeah. So James?
Yes.
I think he wants the explanation of 2D.
If you do the calculation that's asked for in C part, that's a calculation referring to one occupation, say from A to B. You would have a similar calculation available from the occupation from B back to A. So that means if you create the right triangle that involves the two mark-to-mark round points as the slope distance, the horizontal distance as the bottom base of the triangle, and the V or vertical height difference between the two ground marks as the other part of the triangle, you would have one value from going from A to B. You would have another value going from B to A. And just in the same way as you would expect to, say, take the average of things, what would happen if you took the average of those values and made them common for the mark-to-mark values? Well, you would expect things to be improving by a factor of √2. The only problem would be that if, when you're doing something of any appreciable sight length, the problem arises with the effects of vertical refraction. So you may have a different effect on the two different zenith angles, and you wouldn't necessarily be able to resolve that unless you had a reasonably good idea of what the conditions were along the line of sight.
Okay, I have something else. Doesn't shooting both directions eliminate the effect of refraction?
Not if you look at it in the sense of occupying A and then going up and occupying B and sighting back again. The only time that the effect of vertical refraction would be made negligible would be if you had simultaneous reciprocal zenith angles. And simultaneous in the sense that the effect of refraction is the same with both sightings. And you would be sighting the same center as being measured, which is logistically very difficult. So typically, if you can say, all right, the atmospheric conditions are the same for both occupations, then you can say, hopefully, that the conditions are then simultaneous, and you can take the average, and that would remove the effect of refraction.
Okay, so we are still this October 2009 number 5. I don't know if we wanted to deal with that.
Okay. When you're doing a traverse, and you start off on two coordinated monuments, and you close on a second pair of coordinated monuments, how do you figure out the angular misclosure? Well, the easiest way is to take the included angles, convert them into deflections, and if it's a deflection to the left, give it a negative sign. If it's to the right, give it a positive sign. And all of those then algebraically summed together would be your observed deflection from the first pair of coordinated monuments to the direction created by the second pair of coordinated monuments. So that's the observed deflection. If you take the azimuths between the two pairs of coordinated monuments, the first pair and the azimuth between the second pair, and use those to calculate the coordinated monument deflection between the two lines, you have then what we could call the control deflection. Observed minus what it should be, so the traverse deflection minus the coordinated monument deflection would give us the misclosure. And very often that misclosure is given a certain limit, sometimes as a function of the number of angles or sometimes as an actual number or whatever. Usually you don't want to exceed that. So that means that that criterion is taken at 99%. If you then bring it down to standard by dividing by the 99% one-dimensional expansion factor, which you can get out of the chi-squared distribution, which is farther down on the exam sheet, then you have a number that is a limit on the misclosure at the standard level. So then it's a case of taking the uncertainty in the included angles and propagating it into what is the uncertainty in the misclosure. And then you say, well, if we take all of the contribution to the misclosure as being from random sources, then if we measure each angle plus or minus sigma beta, for instance, we should get a certain total plus or minus sigma sub m, which is the uncertainty in the misclosure. And we want that number to be less than the number that we just scaled down from 99%. So then it's a question of, well, how do we propagate from individual angles into misclosure? Well, that's fairly straightforward. You just follow the route that you would have done in the calculation. You take the included angle, convert it into a deflection by adding plus or minus 180 and giving it a proper sign. So that means that the deflection uncertainty is the same as the angular uncertainty. We assume that each one of them is going to be the same at this stage. So we then sum the number of deflection uncertainties together by the number of angles that there are. So if there are 7 intermediate stations, there's an additional angle at each end to make the connection either off or back onto the coordinated markers. So that means there's 9 angles. So there's a factor of root 9 there. And equate the sum into the limit and rearrange it to get the value for sigma beta. That seemed to me to be a calculation that should be relatively straightforward as far as propagation goes, because it's just following through the calculations that would normally be done. And that's why there was a request for the propagation of variance, to develop the expression and to present it. Now, the second part of the question is a limit on the discrepancy between sets. So the angles that are used in the first part to come up with the sigma beta is the standard deviation of the angle that is an average already from however many sets were necessary. So these are the numbers that actually go into the calculation. So they're averages. If we then say, all right, well, if we take a certain number of sets, like n sub s sets, and average those to get the number that eventually goes into the misclosure calculation, then any individual set standard deviation is then improved by a factor of 1 over n sub s to get the average standard deviation, which is the one that goes into the deflection calculation. Now, that means that if we start off with an angle standard deviation, which is basically the standard deviation of the average, how do we convert that into a discrepancy limit for comparing sets? Well, if you remember that if you take a number of items with the sigma sub I and propagate them into what the sigma would be of the average, it's improved by the number of items that goes into the average by the square root. So you go backwards given a certain number of sets to get what the standard deviation would be for an angle that's out of one particular set. And remembering then that the discrepancy for that is the difference between individual sets, so you simply multiply that by a factor of root 2.